Turkey. Hakki, welcome, and I'll hand right over to you, and please start sharing your presentation now. You have about 15 minutes, and we will have 5 minutes of discussion afterwards. Hakki, the stage is yours.
Thank you, John. Good morning, everyone, and good afternoon. Do you see my slides?
I can already see your slides. I hope the audience is also seeing it.
Okay, good.
But I think it's okay, yeah.
Okay, so let's activate the pointer here. Okay. Hi again, my name is Hakki Ozgur. I usually use Ozgur, and this is a study that I have done with my master's student, Batan, who couldn't be here. So, and I am presenting on behalf of him. And our title is again exploring the potential of transfer learning for chatter detection. So this is my quick outline. First, I will introduce our motivation chatter problem, and I will give you a bit background about its solutions, analytic solutions, and intelligent solutions using AI. And then mostly talk about what is transfer learning and how we can utilize transfer learning for this problem. And finally, wrap up with conclusion. So chatter is a problem in a phenomena that we see in machining. Machining processes, as you know, in industry, it's very common. It's backbone of many industries. It is very accurate, very high precision, and you can virtually cut everything, actually. And its efficiency is basically measured with the speed of production rate. Basically, how fast you can machine, it is better. But this is obviously limited by process mechanics, process dynamics. And one of the major limitations here is what we call regenerative chatter. This is a dynamic problem. It's a complicated problem, but there is a brief depiction of the problem here, just to quickly go over it, which is what we call feedback loop for regenerative chatter. So in machining, a lot of chips are produced, and it is assumed that the chip thickness is static. Actually, this is an idealization, but in real life, it's not. Every tooth pass leaves waves on the surface and on the chip as well. So the chatter, which is actually excessive vibration, is caused by two surface waves left by consecutive tooth passes. So when their phase difference is a certain value, actually, with a certain phase difference of these waves, the vibration really wildly increases, and this causes all sorts of problems. The basic problems is obviously the surface quality. As you can see here, this is a surface with chatter, very rough, poor surface quality, and this is a stable cut, shiny, nice surface. And of course, this leads to unacceptable inaccuracy, excessive noise. It also wears out tool very fast. And if it is very high, there can be catastrophic damage to tool or even the machine tool. And it limits the material removal rates, right? The production efficiency. And all in turn, of course, these are also causes waste, material waste, energy waste, waste in terms of production time, so on and so forth. So this is actually one of the major problems, again, limiting machining efficiency. What are the solutions to this? There are two schools of solutions here. First one is analytic solutions, which have been studied by predominant scholars, maybe 1960s, 70s. They are mostly based on model analysis and dynamic modeling of the tool holder, spindle, system, and material properties. They are offline, they are predictive. So you see here an example, fundamental example of it developed by Altıntaş and Budak in 95. So this is a basic 2 degree of freedom modeling of milling. And when this is modeled and solved with vibration-based techniques, it leads to what we call stability lobe diagrams. Okay, so these are called stability lobes, and as you can see, x-axis is spindle speed here, and y-axis is depth of cut, the limiting depth of cut. And what the chart tells us, if you are below the lobe, you are at a stable region. If you are machining higher than the lobe, you are at unstable region. So these regions are unstable. So as a case, if you think that someone is machining with a depth of cut as 6 millimeters with 2000 RPM, it's this unstable region, right? So he has got 2 options: either reduce the speed and go to a stable region, or increase the speed and also go to a stable region as well. Of course, this one is better because you are improving the efficiency, not reducing the efficiency. And again, this is a simple diagram from 95. If you think that today we have machine tools up to 2000, 30,000 RPMs, which means you will have a lot of lobes here and a lot of opportunities to find out stable regions with a very high cutting efficiency. Okay, but of course, these approaches have drawbacks. They are complicated. You need to do model analysis. So this is a basic solution, a simple model, right? So real life is not very simple. For instance, if you are doing a thin wall milling, then the wall dynamics, vibration dynamics comes into play, and the model complicates a lot, right? Gets very complicated. And for 5-axis milling, again, it's very complicated. And another case, if the tool is worn out, then because of the high friction here, process damping effect starts and gets the model more complicated. So even with a small change, what I'm trying to say is, if you change the tool length here, the solution is invalid. Now you have to generate a new SLD diagram. So the variability in manufacturing is a problem here, and a simple change system alters the dynamic model and the process mechanics. Hence, it changes the stability lobe diagram. So for every different case, you need to either make a new model or at least do the model analysis to collect the system constants here from scratch. Obviously, this is not very feasible for industry, for everyday machine shop. This is a lot of time to spend for improving efficiency. So to mitigate these effects, actually, the other school here is intelligent chatter detection using AI, right? So here we are talking about artificial intelligence techniques. Mostly earlier it was machine learning, KNNs, ANNs, decision trees, SVM. And today we are recently talking and applying these techniques, right? Deep learning, CNN, LSTM. And these systems are, in nature, they are online. So online physical quantities are observed, such as vibration, acoustic emission, cutting force, power, and they are collected by some sort of sensor, and they are consumed by an intelligent processing and learning technique, which aims to provide timely information to adapt the process parameters to avoid chatter. So I will show you some typical examples. For instance, for machine learning method, to understand the advantages and disadvantages of it. For machine learning, we would typically have, collect the data, do the signal processing, and after that, there is a tedious and lengthy feature stage, feature generation, feature selection, the feature engineering stage, which is critical actually for success of classifier here, and then the decision can be made. So the advantages here are the maybe tedious feature engineering stage, and manufacturing variability is still a problem here because again, if you change any constants here like tool or work material or machine, so the performance of the classifier will degrade. You need to do maybe your feature engineering again, so on and so forth. And so this comes down to latest big thing, deep learning. So it has got some advantages, right? Like the biggest advantage here is with some deep learning methods. As an example here, CNN. This is the study that we have done recently. You can eliminate the feature extraction stage. So CNN actually extracts the feature itself. And here we use just for all the signals that we collect, we applied a continuous wave transform and feed them to CNN. Here we actually, the existing problem with most of the supervised DL methods, the data labeling problem exists. So you need high amount of data for better accuracy and you need to label them. How you are going to label it? Here we combine the analytical methods. We produce the SLDs and use those in labeling. Okay, and we have quite successful results here, but the variability, it's also a problem. Still, if you change the system parameters, variables, your performance will degrade. So now this brings us to concept of transfer learning. It's emerging, rather new, but it's successful mostly in real-world application. So what is the idea here? It's the transfer learning is the idea of mostly solving the data scarcity and data collection cost problem in one domain by utilizing knowledge learned in another domain. So the basic idea is simple. With traditional ML, for a domain or task, we train a model. If we change the domain or task, we collect again new data, we train another model, again from scratch. But what transfer learning suggests, you have a source domain and target domain, collect data for the domain and task from the source, and you can use it with some techniques, some clever techniques. You can use it with another domain, which would save you time of data collection and cost of data collection, etc. So it's yet emerging. If you look into its details, the categories here, there are different categorization. One is based on its features, whether they are similar or different. The other categorization is based on the continuity, whether it's a one-time transfer or a continuous transfer. But most accepted categorization is based on the domains and labels. Whether, for instance, with inductive transfer learning, domains are same, tasks are different, but you have available labels. With transductive, source domain has only large amount of data, but for the target domain, you don't have any available labels for the data that you have, even if it's few data. For unsupervised, you don't have any labels at all, and very similar to inductive, but this becomes an unsupervised learning problem now. So such categorizations exist. So if we look at from this perspective to machining, we are trying to identify some strategies for chatter detection, and I will summarize these, which a few exist in literature, a few of them we have done. But to understand these better, if you look at machining, like it's very variable, right? There are many different types. For instance, turning and milling, or broaching, or grinding. These are different domains, and in each of them we have different tasks, like outer diameter turning, boring, facing, or milling, like slot milling, shoulder milling. So all of the dynamics change with these different tasks, and also tool holder, tool and holder workpiece, cutting parameters. These are the features that can change, and what we measure, vibration, sound, or maybe current, whatever power, they can also change. So we have all this variability, and actually there are a lot of opportunities here to transfer, one learning from another. So what do we have in hand? We have a few studies actually until now, very recently in literature. This is a simple one that we have done for this paper actually. So this can be called as cross-cutting parameters. We collected two data sets here. The difference is only one cutting parameter, which is the radial engagement of the tool. For the first data set, it is 50%. For the second one, it's 75%. And we use the SVM classifier for this. So we have 3 steps. With the pre-training and testing of it, we use only data set 1. So with this transfer this model, we directly test it with some part of data set 2. And as a third stage, which is fine-tuning, we mix some part of data set 2 with all of data set 1, and then test it with data set 2. If we look to the results actually here, as you see, pre-training, it's the first only data set 1 case, it's quite high. After we transfer, the accuracy drops to 84%. When we fine-tune it, it's again raises up to 92%, which is actually what's expected. So another strategy, very recent, by Yeşilli et al. From literature, is Crosstool. Here, what they have done is basically they didn't change the tool, but they played with the dynamics of the tool. They changed the length of the tool, which affects the dynamic results, and investigated the performance by different machine learning methods.
Hakki, 1 minute, please, to wrap it up, because we're at the end of the time.
Almost done. Okay, almost done. So they find out that random forest gives the highest performance. And maybe this is the last and most advanced strategy, physics-guided strategy, because it really decreases the need for data collection. The idea here is for pre-training a simulation data set based on some kind of theoretical model. Here, Postel et al. Used reception coupling model approach to simulate the data, and they used ANN basically. After pre-training, they fine-tuned it with a small experimental data set, and then they done their prediction. And finally, similar to that, this is a work, physics-guided work that we have done, which is a bit more successful in terms of accuracy. Here we use CNN, a deep learning method, and we use the model-based simulation technique again, and automatically label the data using the stability lobe diagrams, and convert them to images with Hilbert-Wang transform, and train the AlexNet. And then we transfer it directly, subject them to measured data for classification. So lastly, this chart shows the comparison of these very few works in literature up to now in this area. This is the final one that we have done. We have quite high accuracy, between 82% to 100, and a bit better than the others here. And yet we are only using simulation data here. So literally with this approach that we have, there was no data collection at all, which of course makes the job very applicable to industry. So as a conclusion, if I just wrap up, chatter is a well-known problem, old problem, but it gets complicated when machining technology advances. So better machining technology actually complicates the chatter. You need new models and etc. Both of these analytical techniques and AI-based systems, the bottom line is they are sensitive to variability in manufacturing, particularly machining. That creates a barrier to industry adoption. And here we feel that transfer learning approach, we are trying to demonstrate the effectiveness of it. And its real world applications, it's proven to be effective. And this can provide a solution to variability in manufacturing by reducing or even completely eliminating the data collection requirements. Obviously, for future works, there is a lot of variation. Yeah.
We are almost out of time.
Okay.
So please, last
and I am
sentence.
done actually. So future works, continue study more on this area. There are a lot of things to be done. So I should acknowledge TÜBİTAK, Turkish Scientific Research Council, which is funded this study. And these are a few good references that we benefited from. And thank you very much for bearing with me.